So we are picking up where we left off last time, talking about deceptive alignment today. If we recall, last time we sort of started establishing this case for why deceptive alignment might be a problem, why it might happen, and today we're going to try to pick up with that and really go into a lot more detail on what the case for deceptive alignment might look like. Okay, so let's just recap. So what is deceptive alignment? So one thing I really want to get out at the beginning is just some things that it's not. So one thing that deceptive alignment is not is dishonesty. So we're not talking about a situation, any situation where you have some model, some AI system, and that system lies to you, it tells you some false thing. There are a lot of situations where that might happen, but the situation that we're concerned about is deceptive alignment, which is specifically the situation that we talked about last time, where the reason that the model is doing a good job in training, the reason that it looks aligned, the reason that it's pseudo-aligned, that it sort of seems like it's doing the right thing, is because it is actively trying to accomplish some other goal other than the one that we want. And because it eventually wants to do some other thing, it's pretending to look aligned in training for that purpose. OK. And so in this sense, this is sort of why we were talking about it last time as this sort of form of pseudo-alignment that only arises potentially or that can arise even in the case where you've sort of trained away everything that you can with adversarial training. Though we're not necessarily going to be talking about it just in that context here. We're just sort of talking about any situation where the reason that the model looks aligned in training is because it's trying to accomplish some other goal. OK. So one analogy that I really like for this is from Ajay Kocha. So the idea is, let's say that I'm trying to run a business. And I'm a child. I just inherited this business. And I need to select somebody to run the business for me. But I'm a child, and so I have a very difficult time actually being able to do that selection. Here are 3 different types of people that you might find in your selection process. We have saints. These are people who really genuinely want to help you run the business. We have sycophants, people who want to do whatever it takes to make it look like they're doing a good job running the business, but don't actually care about making the business good. And you have schemers, people who want to use the business for their own purposes, and so want to fool you into thinking they're doing a good job. And so in the deceptive alignment case, we're specifically talking about schemers, right? Both sycophants and saints might lie to you. But schemers are specifically this deceptively aligned case. They're the case where they have some objective that is different than what you want. And the reason that they look like they're doing the right thing is because they eventually want to do some other thing that is not what you want. OK, does this all seem clear? Great. OK, so we want to understand how likely is deceptive alignment in practice. So the problem is, as we sort of were establishing last time in terms of why deceptive alignment might be such a problem, even the limit of adversarial training, is that deceptive alignment and robust alignment in a situation where the model is actually doing the right thing are behaviorally indistinguishable, at least during training, right? No sort of input that I could possibly generate would necessarily be able to always distinguish between them, right? We saw things like RSA 2048 last time, where there are examples of cases of a thing that a sort of deceptively aligned model could look for to tell whether it was in training or deployment that we could never possibly actually produce an example of during training. And so because they sort of both look the same, because they're sort of both trying to do the right thing, one just for nefarious purposes, the question of which of these 2 models we get is going to be a question of inductive biases. It's going to be the same sort of question we started this whole thing off with, of trying to understand what is the structurally simplest model? What is the sort of model that is the one that would be selected for by gradient descent by our neural network, that would be sort of simple to implement, that would be most likely to find? Yeah, question.
So it seems pretty clear that the outputs of a deceptively aligned and robustly aligned model would be the same in training, so there's no way to tell the difference. But how do you feel about cracking open the model and actually seeing the cognition inside, the interpretability field that's filled in? How do you think that's likely to work? Do you think that's just doomed to failure? What is your opinion on that?
Yeah, that is a really great question. I think my answer right now is going to be, we're going to imagine we have no interpretability. We're going to be like, imagine we're in the situation where we can't look inside the model. The only thing that we know is that it is some algorithm that we found that actually does a good job on training. And that algorithm is going to be whatever algorithm is most favored by the inductive biases of our training process. Whatever is the structurally simplest thing that is the largest basin, whatever. Theoretically, there might be things that we could do to try to change that default picture, right? There is some default picture that is if we just plow ahead with machine learning with the exact same sort of inductive biases that we generally use by default, and we don't make any changes to try to adjust for avoiding deceptive alignment, what happens, right? Now, that's not entirely realistic in the sense that we probably will do some things to try to adjust for it. And we'll sort of talk at the end about what that might look like and in later sort of lectures as well. But right now, I just want to establish what is that default case, right? And so transparency interpretability, trying to look inside, do something to actually try to detect whether it's deceptive or try to find some way to avoid deceptive aligned cases is absolutely something we may want to do, but it's not something I'm going to be talking about right now. We're just going to be sort of trying to understand what this sort of default case is. OK. Great. OK. So again, just reminding the analogy from the first time, right, is we're sort of thinking about this case where there's sort of two possibilities. We could learn the color classifier or we could learn the shape classifier. And they both look the same in training. They both sort of do a good job on these particular training examples. But in some particular deployment examples, in some other cases, they do different things. And the deceptively aligned model and the robustly aligned model are very similar, right? They sort of always do the exact same things in training. Every example that we can check, they both look like they're trying to do the right thing. But if the deceptively aligned model sometimes finds itself in a situation where it has the opportunity to break away from whatever processes we have to prevent it from doing something bad, then it's going to do something bad, right? Once it's in deployment, once it's out there, it might do something very different. And so, again, if we want to try to answer which one of these models we're going to get, we have to answer the same sort of question that we sort of started the whole series with of how do we distinguish between which of these models we're going to get? How do we distinguish between getting the algorithm which is doing shape classification and the algorithm which is doing color classification? OK. So this is a really difficult question, as we sort of have already established. It's really it's not trivial to understand the inductive biases of these machine learning systems. And so in the sort of face of uncertainty, I think one thing that we can do that is really helpful is try to sort of do case analysis, right? We can say, OK, we don't know exactly what the inductive biases look like. We don't know what is sort of going to happen. But we can suppose that, well, here are two possible scenarios for how to think about which sorts of algorithms are favored by machine learning systems. What does it mean to be structurally simple? What does it mean? How do training processes select for which algorithms they choose and which ones they don't, and sort of see what consequences we get in each scenario. And if we sort of have robust conclusions across various different possible ways of thinking about the inductive biases of our machine learning systems, then we can be more confident that even though we're very uncertain about what it actually is that is causing which algorithm we get over the other, that we still at least have some conclusion that is meaningful. So that's the idea. We're going to sort of break things up into two cases. So we're going to call these the high path dependence case and the low path dependence case, where effectively these sort of represent two ways of thinking about the inductive biases of machine learning systems, two ways of thinking about why you would get one algorithm over the other, why you would get the color classifier over the shape classifier. OK, so here is story number one. This is the high path dependence world. So in the high path dependence world, we're going to say, well, different training runs can converge to very different models depending on the particular path taken through model space. So depending on exactly how we set up the initialization, it really matters sort of what basin you're going to end up in really matters how you walk around that loss landscape, right? That there might be multiple basins that you could fall into that are of similar sizes, and which one of those basins you're going to find really depends on your initialization and the exact sort of path that you take. Another way to think about this is it's sort of very sequence dependent. So maybe we start with learning one particular algorithm as like one of the circuits in our model. But then to learn some additional algorithm, well, an additional circuit will only be learned if it's helpful, given that we already have the other existing circuits. And if it isn't helpful, given the things that we've already found, then we won't find it. And so we're sort of thinking about things as, well, okay, we have to first find some individual thing which is incrementally helpful, and then other things which are incrementally helpful building on top of those other things that we found previously. And so we sort of are imagining our model being built up in this sort of iterative process, and an iterative process that is potentially very sort of path dependent. It's a process that is can vary quite a lot depending on exactly which things we build up first in the model. Okay, yeah, question about this.
Last week you mentioned that induction heads were engines that were built from transformers, and they occurred not immediately in training, but at a relatively predictable point, and they basically always happened. Wouldn't that suggest that transformers training are sequential, but also low path dependence?
Yeah, that's a really good point. So I think a couple of things I'll say to this. So first, I'll say I think induction heads are some amount of evidence, at least against path dependence in the case of induction heads, where it seems like the induction heads really always form regardless. Though I also agree that there's sort of two things that I'm conflating here. There is a extent to which things all converge, or diverge, depending on how I set it up. And there is, should I think about things in this, sort of piecemeal way where we're adding things on top of other things? It could be the case, theoretically, that the best way to think about in the inductive biases is, will they always converge to the exact same thing? But the way to understand what they converge to is to try to do this analysis of, what circuits would be good to build upon other circuits. But it'll always end up being the same circuits. That's totally plausible. I think that the thing that I would say is that I think that that's a little bit less likely. If it is the case that the inductive biases sort of do, the correct way to think about it is this sort of iterative process, then I think we should expect on average things to diverge more and to diverge, to sort of converge more in the other case that we'll talk about in just a sec. So, but I don't mean to say that these sort of two cases are comprehensive. Is maybe the key point here is that we're going to be talking about two possible cases, and each one bakes in a bunch of assumptions. You could alternatively separate out just a couple of those assumptions and mix and match and try to run the analysis again and see what would happen in that case. I think that would be a really valuable thing to do and would help give us even more confidence or less confidence, depending on how things go in terms of what the sort of overall structure of different conclusions from different types of inductive biases. But for our purposes right now, we're sort of looking at these sort of two very broad and disparate categories, where one is like very high path dependence, things are very sequential and very divergent, and the other one is very low path dependence, which is going to be things are very convergent and very non-sequential. We'll talk about it a bit. And so hopefully the idea is to sort of cover as much of the space as possible. But I absolutely agree that you could imagine something more in the middle that sort of mix and matches some of these properties without the others. They're not necessarily like these are the only two ways to think about it. Okay, and I also want to point out that both of these views that we're going to talk about have, I think, a bunch of empirical evidence supporting them. So if we think about the high path dependence view, some empirical evidence that I think supports the high path dependence view. There's Birds of a Feather Do Not Generalize Together, which is a paper that found if you take a bunch of different fine-tunings of BERT, which is a language model, that sometimes they can have really disparate generalization behavior, really disparate behavior on new data points. This very often happens with reinforcement learning, because reinforcement learning can be really path dependent in the sense that once I get a particular policy, which additional changes to that policy are helpful are really dependent on what moves is the thing going to make after I make this move, right? So if we think about playing Go, making a particular move might only be helpful if I know how to follow it up, right? And if I don't know what the correct next move is after that move, if I don't know the sort of whole line, then making that one individual move might not actually be helpful. And so there can be a lot of sort of additional path dependence in reinforcement learning. And so there's some evidence like this that sort of points us into thinking that maybe high path dependence is a good way of thinking about the inductive biases of machine learning systems. Okay. But it's not necessarily the only way. So the low path dependence view is also, I think, quite plausible. So how do we think about low path dependence? So the idea of low path dependence is, so everything sort of converges to the same sort of unique, simple solution, regardless of how we set up our training process. So why might we think that this is true? Well, this is sort of going back to what we were talking about at the beginning about really disparate basin sizes. Some basins can be much larger than others and really heavily favored over others. And so we can be in a situation where maybe theoretically you could end up in any basin, but effectively, for all intents and purposes, there are going to be these structurally simple algorithms with really, really large basins that dominate the loss landscape and sort of force essentially all paths into them. And furthermore, in this case, we're going to be sort of thinking about how to understand which algorithms are these sorts of, occupy these really large basins, as just trying to understand this basic question of, which algorithms are structurally simple, right? These sort of basic properties of the algorithm, right? Global properties about, if I look at the final algorithm, can I understand how simple is it? How many sort of, distinct pieces does it use? How many free parameters does it have? To try to understand how likely it is. And so in this case, we're imagining we don't have to think about this sort of, piecewise iterative process where we're not imagining that, first you develop this thing and then you develop that thing. We're instead imagining, let's just think, if we look at the final algorithm and evaluate some metric of, how simple, structurally simple is this final algorithm, from that we can determine how likely it is for that algorithm to be the one that we find from our machine learning process. And so this is sort of, a different way of thinking about it. I think it's, again, also quite plausible and supported by lots of evidence. We talked sort of, in the first lecture about stuff like grokking, where, you have this case where if you just keep training, eventually you just, snap into this one really structurally simple algorithm that sort of dominates the landscape after a bunch of training. And we can also think about this is the Mingard et al. Line of work, where what they find, this is another sort of piece of evidence in favor of low path dependence. What they find is that they take a sort of approximate model of what it might look like to have low path dependence, which is take a randomly initialized neural network where we just sort of select each parameter from a Gaussian, and you just keep randomly initializing your neural network over and over and over and over again until you stumble upon a random initialization which actually does a good job on the task. Now, this is not practical to ever do in practice, but you can sort of approximate it via various approximations, and you can measure if you theoretically did this, if you just kept doing random initializations until you found one that did a good job, how close is that to what gradient descent does? And if those two things are very close, it implies a form of low path dependence, because it implies it doesn't really matter the exact path that gradient descent takes. It only matters the sort of, how, likely is it on the random initialization, which is sort of a proxy for, how structurally simple is the algorithm. Because as we sort of talked about at the beginning, structurally simple algorithms have more implementations in parameter space. And they find that these are very close. And so, that's some additional evidence in favor of the low path dependence view. Okay, so I think that these two overall views are plausible. Again, they're not the only views, right? There could be other ways of thinking about, inductive biases. They're definitely not, exhaustive, but they are like two very different views. And so we can sort of, try to understand what happens in each case as a way of sort of covering the space, or at least, trying to get, different conclusions from different places. Okay, great. Okay, so we're going to start by trying to understand, going back to the reason, the thing we're trying to talk about is deceptive alignment. So the first thing that we're going to do is we're going to try to understand what is the likelihood of deceptive alignment in the case of high path dependence. So we're thinking about, specifically inductive biases in this high path dependence sense, where it really matters the exact order in which we develop individual circuits and individual ways in which things can be very divergent. And we're trying to understand, in that view, how likely is the development of the deceptive alignment algorithm, right, as opposed to the robustly aligned algorithm. In the same sort of sense as we're just thinking about, shape versus color classifier. Okay, so we need to, get a couple of things out of the way in terms of, how we're going to be comparing, various different model classes here. So we're going to be supposing that our training process is good enough that for our model to be able to do a good job, it has to sort of fully understand the thing that we want. This is sort of very similar to what we were, talking about at the end of the last lecture about, the limit of adversarial training, where, if we can do enough adversarial training, if we can give it enough examples of different possible situations that it could be in, we can eventually sort of, get down to only a small section of possible algorithms that are able to, fit all of the examples we can give them. So, we're not going to be thinking about algorithms like, where it's doing like the maze thing, where it's trying to go to the green arrow rather than the end of the maze. Because in that example, we can just train on mazes that have the green arrow in a different spot, right? And we can sort of force it to try to do the right thing in that case. And so we're really only considering models that, even in the limit of every possible example that we can generate in training, it still looks like it does the right thing. And importantly, like we talked about last time, this is going to include the deceptively aligned model, because of structural facts like RSA 2048 mean that there are always going to be, facts about the world which are easier for our model to check than there are for us to generate, which means even the limit of our ability to generate as many possible things as we can, there will always be sort of properties of the world that a deceptive model can look for to sort of tell whether it's something, it's a test example that we generated or a real thing in the world. And so even for all the possible things that we can generate, the deceptive model is still going to be there. But it does get rid of a bunch of these sort of bad models that don't really understand the actual goal, right? They're just trying to do some proxy for the goal instead. OK, yeah, question.
This idea of doing enough adversarial training so that you end up with a training process that the model fully understands what we want, whether it cares or not. How likely do you think we are going to get that in practice as we get smarter machine learning systems?
Yeah, so I think that eventually the thing really should understand what we want, right? There is sort of some finite complexity of the actual desirable thing that we're trying to get it to do. And as your model becomes better and better at understanding what it is that you're trying to accomplish, eventually it's going to understand. Now, we talked last time, right, about there's at least two mechanisms for doing that understanding, right? It can understand it just via internalization, where it has some internal understanding and eventually gradient descent just sort of adds it. Or it can happen right through modeling, where the model is just trying to understand the world. And in understanding the world, eventually just figures out enough facts about the thing we're trying to get it to do that that's the sort of process via which it learns the information about what we're trying to accomplish. But eventually, as we make more powerful AIs that are better and better at understanding things, eventually they're going to figure out facts like this, facts like the thing we're trying to get it to do. Now, one of the really important things, right, and we're going to be talking about this a bunch, is that it really matters, in the high path dependence view at least, it really matters the ordering of which one of those two sort of paths comes first. Do we get the internalization first, where we first gain the understanding internally, where it's gradient descent just sort of directly replaces the existing proxy with the thing we're trying to get to do? Or does the modeling happen first, where it learns and understands enough facts about the training process to figure out what we're trying to get to do that way? But either way, eventually, we're sort of going to imagine that, as AIs get better, this should occur. OK. OK. So how are we going to be comparing different model classes, right? Different types of algorithms that have the property that they sort of fully understand what we want. So in the high path dependence case, there's sort of two main things we're really going to be looking for. We're going to be trying to understand from each step that it takes to sort of get to that algorithm, how much marginal performance improvement do we get? As we're sort of going along, walking through this loss landscape, how steep is that path down the loss landscape, to this sort of algorithm, right? How much performance improvement are we getting along the way? And the reason this is important, right, is that gradient descent is going to take the steepest path. And so we really want to understand, is this actually, giving us large incremental performance improvements as we're sort of progressing towards this type of model? And then the second question we want to understand is how many steps are needed, right? If it's going to be really, really difficult for us to eventually reach the desired that particular model class, it takes a bunch of steps. That's going to make it less likely. If it's fewer steps, that's going to make it more likely, because we're sort of imagining that, well, in this high path dependence case, the more steps that you sort of sequentially that you have to take, the more steps that it could end up taking some different thing instead. And so fewer steps means it's going to be more likely. OK. So these are the sort of things we're going to be looking at in the high path dependence case, where we're sort of thinking about inductive biases in this high path dependence sense. The things that we're going to be looking at to understand how likely it is that we get a particular model class, a particular sort of set of possible algorithms, are these sorts of factors. OK. Question?
Yeah, sorry. So what follows from big steps? So in point one, what does it mean that in every step there is a big improvement? Which direction this is an evidence for, and why? Good.
Yeah. So the idea here is that if we're thinking about a loss landscape, where each individual possible setting of the model parameters corresponds to some particular algorithm which has some particular loss. As we're sort of traveling around this loss landscape, there's some basin that has perfect loss or whatever on this. It fully understands what we want. And for each model class, we're going to be looking at different sorts of basins. And we're going to try to understand what does the path from some random initialization to that basin look like. And then based on that path, we want to understand how likely is that path under this sort of high path dependence view. And if we're thinking about it, well, OK, so what would make a path really likely to be selected by gradient descent? Well, one of the really important factors is the steepness of the path. Because the thing that gradient descent will do is it will select the steepest improvement at each individual point. That's sort of structurally what gradient descent is trying to do. It's looking for the direction of greatest marginal performance improvement and then stepping along that direction. And so because of this sort of basic understanding of gradient descent, we're going to be thinking about looking for large marginal performance improvements along the path as being evidence of the sort of path that gradient descent would want to take in this sort of high path dependence view. Okay, yeah, more question.
So it seems that this marginal performance improvements per step is like a relative measure compared to other steps that the model could take at any point, right? It's like, it seems like kind of hard to tell absolutely for a given training run or a model pass, like, will we get the high marginal performance improvements per step or not? Like, what's the way we could start approaching this question?
Yeah, that's a really good question. So I think that you're sort of anticipating one of the things we're sort of going to talk about, which is, well, I'm going to have to make a bunch of assumptions. And I think the way that we're sort of going to approach this is we're going to say, here are 3 particular paths, and then we're going to just compare those paths. And we're going to see, at which point do those paths diverge, and when they diverge, which has the strongest marginal performance improvement, right? And that's not in general the right way to do it, right? If we really wanted to solve this problem properly, we would need to integrate over all possible paths, right? But that's really hard, and so we're not going to try to do that right now. We're just going to look at sort of 3 example paths and try to compare, the individual probabilities of those specific paths, and from that we'll, try to draw some sort of general conclusion. But obviously that is a little bit, we have to be a little bit wary of that because it's not literally correct, right? We aren't actually doing the full analysis. If we wanted to do the full analysis, we really would have to do sort of what you're talking about and look at all of the possible paths and really try to understand each one. So we're going to be doing an approximation. Okay, cool. All right, so I just said we're going to be comparing 3 different paths. So those are going to be 3 different paths to 3 different model classes that we're going to be sort of trying to understand. These are probably going to be a little bit familiar from what we were talking about at the end of the last lecture. I'm going to introduce a new analogy to sort of help us really get our heads around these. So we're going to suppose that in this sort of analogy that you are the Christian God, and you want to get humans to follow the Bible. And so we want to understand what are the sort of humans that generally do a good job at following the Bible. Okay, so here is an example human that does a good job at following the Bible, is Jesus Christ. So why does Jesus Christ do a good job at following the Bible? Well, in the sort of Christian ontology, the idea is that Jesus Christ is essentially the same as God. He's sort of a copy of God in some sense, right? And so Jesus Christ does the right thing because Jesus Christ just has the exact same beliefs, the exact same goals as God, right? And in that sense, therefore, because God wrote the Bible, Jesus Christ is going to follow it, right? So this is like one type of human that you can imagine in this sort of analogy. Okay, there's others though, right? So another example would be Martin Luther of Protestant Reformation fame. Martin Luther, he wasn't the exact same as God, but he really cared about trying to understand what the Bible said, and so he put a bunch of effort into reading it and trying to understand it. And he thought it said some different things than other people did, and so he nailed a bunch of theses to a wall. But the basic idea, right, is that he put a bunch of effort into trying to understand the Bible and really cared about doing whatever it was that the Bible said he should do, right? And so that was another type of human, right, that is in fact really good at doing what the Bible says. Okay, but it goes through a different route, right? Rather than Martin Luther just inherently having the exact same goals and desires as God, Martin Luther wants to figure out what desires God has from reading the Bible and then do those. Okay, and then we have human number 3, which is Blaise Pascal. So Blaise Pascal of Pascal's wager fame, he doesn't necessarily know whether God is real, but he's like, I think that if I went to hell, it would be really, really bad. And I think there's enough probability that I could go to hell that I'm going to try to do a really good job at what the Bible wants me to do. Not because I actually agree with the Bible or want to do the things the Bible wants to do, but because I think if I don't do that, I might go to hell. And so Pascal does not, unlike Jesus, who really, cares and has the same values as God, and unlike Martin Luther, who really wants to figure out what God actually desires, Pascal doesn't care about what God wants. He just doesn't want to go to hell, and so he's trying to avoid that outcome by, attempting to play along and do what God wants him to do. Okay, So if you've been paying attention, you probably know where I'm going with this, which is we can think about each of these as mapping onto one of the categories of that we were talking about at the end of the last lecture, right? Where we can think about the Jesus Christs as the internally aligned models, the Martin Luthers as the corrigibly aligned models, and the Blaise Pascals as the deceptively aligned models. Where the idea is that the Jesus Christ sort of internally have the exact same values as the ones that we're trying to get. The Martin Luther models, they try to figure out what we want and then do that, but they don't necessarily, have exactly the same beliefs. They just eventually figure it out by, trying to understand what we're trying to get them to do. And the Blaise Pascals are deceptive. They actually want something totally different, but because they're afraid the training process is going to punish them, they play along. Okay. So these are going to be the three model classes that we're going to be trying to understand the likelihood of sort of getting to. Question.
Do we believe that the Martin Luthers will eventually become Jesus Christs, or that the problem in this case is just too difficult to solve, and so a corrigibly aligned agent can't actually become internally aligned by just knowing more?
So in this case, so it could be that you start from a corrigibly aligned thing and you become internally aligned thing, but it's not necessary. So in this case, we're imagining that all three of these model classes are model classes which actually fully fit the data perfectly, right? So these are all cases where each one of these actually is able to do everything correctly in the training data. And so it's not like the corrigibly aligned one is sort of making a bunch of mistakes and therefore it needs to become internally aligned. What we're going to be imagining is that the corrigibly aligned one actually does know enough facts about what the Bible says, what we actually wanted to do, that it's able to successfully figure out what it is that we wanted to do in each case. And so because of that, it's not going to be the case that these are going to differ in performance. And so it may be that you start from corrigible and you go to internal, but if that were to happen, it would have to be a fact about the inductive biases, right? It would have to be something like grokking, where they both actually fit the data in training, but eventually you shift from one algorithm into the other, which might happen, and we'll talk about why you might end up with one or the other. But it wouldn't happen in this case where we're imagining it just because the corrigibly aligned one isn't able to fit the data.
So the corrigibly aligned one basically is internally aligned with respect to the training data, but not necessarily with respect to the real world.
No. So internal alignment does not mean is aligned, right? Internal alignment means, in this case, something very, very specific, which is it internally has directly hard-coded into the algorithm, into the weights of the model, the exact objective that we are trying to get to accomplish, right? That is what internally aligned means here, right? So it is not like it's internally aligned with respect to one thing or not the other, right? The idea here is that all of these models look aligned on training, but the reason they do a good job is different, right? The internally aligned one does a good job because it directly, as a part of its algorithm, defines what it means to do a good job in exactly the same way that we would define it. The corrigibly aligned one does not do that, right? It doesn't have some part of the algorithm, some part of the model where it defines exactly what it means to do a good job according to what humans want. Instead, it just sort of defines what it means to figure out how to do a good job according to what humans want. And then it sort of figures that out based on understanding what we've written and what we've told it in a bunch of facts about the world, right? And then the Blaise Pascals, they just encode for some other random objective, and then they have to figure out, to be able to accomplish this other thing that I really want, I'm going to need to play along in training. Yeah, question.
Feel free to tell me that this is a question for Q&A, because it seems my derailless further, but here we assume that the model does fit the training data perfectly, it basically understands exactly what we want. So I guess, first of all, would you say that the currently most strongly aligned models fit any of this? With my guess being maybe corrigible for ChatGPT style models. And do you think it's valuable at all to think about which of these it's closer to, and to think what's the current path, and to factor in the current trajectory of training before we start just assuming that okay, we have converged to something. What is it? Do you think it's valuable to think about the current process?
Yes, in terms of is it valuable, the answer is definitely yes. In terms of are we going to talk about it right now, a couple of things. So the first thing I'll say is that I think I would not describe the best models that exist right now as being able to fully understand the thing that we want. They don't do that, right? There's just lots of cases where they clearly are not doing the thing that we're trying to get them to do, and so they're sort of not yet in this limit of adversarial training. And so they're not any of these model classes right now. They might eventually become one of these model classes, but right now they're none of them because they don't actually, they're not actually in this limit yet. We're going to be talking about a lot of these, all three, the sort of paths that we're going to be looking at in the high path dependence case for all three of these. Often they're going to look like they start out in very similar cases. And I think that that starting point is at least sort of defined by what we think current models are doing to some extent. I think that for large language models in particular, the story is a little bit trickier because it's unclear if they even sort of have proxy objectives in a meaningful sense. Later on in another lecture, we're going to talk a lot more about theories for like what internally might large language models be doing and how to think about that. I think it's a very particular case, but I don't want to talk about it right now. So we're mostly going to be imagining that the sort of arguments we made in the last lecture about like, it's going to have some sort of a proxy, Mace objective, mostly go through. I think it's unclear the extent to which those arguments go through and what they sort of imply about, current large language models, but we will return to that specific question later on in another lecture. Okay, yeah, question?
So I think I understand why it's hard to distinguish between Pascal and the first two during the training, but don't Jesus Christ and Martin Luther behave differently during training? Don't Martin Luther ask more questions? Even like it depends on what kind of training we have, but I imagine that even the training can be somewhat interactive, and I would imagine that a corrigible model would even towards the very end of the training would ask a lot of questions. Okay, is this what you mean? And the internally aligned will just do the perfect job without questions.
Yeah, that's a good point. So I think that the thing I would say is that is possible, but it is also possible that the cordially aligned one just already knows those facts, right? It may be that it already knows all of the relevant facts to understand what it is that we want it to do, but it has to actually figure them out, right? So we think about in an individual, run of the model, the internally aligned one just starts knowing exactly what it needs to do. The cordially aligned one doesn't. It starts knowing that it needs to figure out what we need to do, and then it goes and looks in like wherever it's keeping its knowledge, and it has a bunch of knowledge, right? And it's like, I understand these facts about the world. Based on these facts about the world that I understand that in this case I need to do this particular thing. And so it could be that it already has that knowledge. Because we're sort of imagining this limit, we're going to be, I think, mostly imagining a situation where it already has the knowledge. I'm also basically just going to imagine they all already have that knowledge because, again, in this limit, to be able to do a good job on basically all of the possible tasks that we can give it, it probably just has to understand tons and tons of facts about the world and just sort of understand those to start with. And so we're just going to be mostly imagining that it just sort of already has all of this knowledge. Okay, yeah, question?
When we talked earlier about like path dependence, which was entirely dependent on the training process itself, but now we're just assuming that that training process is already done and we already know everything that we need to know. I'm a bit confused at that change.
Yeah, so maybe it's not clear. We haven't talked about the paths yet, right, to get to these. I'm only talking about the model classes, and then very, very soon, we're going to talk about what a path might look like to get to each one of these model classes, okay? And then we'll try to understand how likely each one of those paths are, okay? Great, okay, let's do that. So we're going to start with a path to internal alignment, right? So we're in the high path dependence world. We want to understand how likely is this model class for the internally aligned model. And to do that, we need to understand, what does the path look like to get there? So I said previously that all of these sorts of paths are going to start in a pretty similar spot. And so the place that we're going to start is we're going to start with this sort of proxy aligned model. So we talked about this a bunch in the last lecture, the case where you sort of have this Mace optimizer and has some proxy objective, right? It starts with some goal like, go to the green arrow rather than go to the end of the maze that is correlated with the thing that we want, but not exactly the same. And then we want to understand, starting from a model that looks like that, what directions are you likely to go in this sort of high path dependence view? Okay, so in the internally aligned path, what we're going to imagine is that gradient descent is sort of going to continually improve that proxy, right? It starts with some bad proxy, that is sort of correlated. It has some facts about what it is that we're actually trying to get to do, but it doesn't actually fully sort of correspond directly to the thing that we want. But it keeps on modifying it because if it had a better proxy, it would have better performance on various examples, right? If we think about the case of the the green arrow, if we can give it an example where it actually has to do the right thing on the larger maze with the green arrow in the wrong spot, then it's going to have better performance if it has a better proxy. And so gradient descent keeps making the proxy better and better until eventually it sort of fully fits the data. And furthermore, for the path to internal alignment, we're going to imagine that that process of sort of iteratively improving the proxy happens before the modeling process, right? We talked previously about, there's sort of two paths via which all of this information about the thing we're trying to get it to do could enter into the model, right? It could be that it just, in general, understanding the world better is good for doing a good job on almost any task. And so there's going to be, pressure to just understand the world better. We're going to imagine in this case that most of the pressure that causes it to understand the proxy, it sort of first happens, via just direct pressure to make the proxy better, because having a better proxy lets you do better on some examples, rather than the sort of having a better world model, understanding the world better causes you to do better on examples. And so because of this, we're sort of imagining in this case that first your proxy gets better and better until it sort of directly corresponds to the thing that we want, before your understanding of the world gets better and better and better until you fully understand exactly what the training process is trying to get you to do and how the training process works. Okay, and we'll see sort of why that's important, because if we have the opposite ordering, then we're sort of going to end up in one of the other paths. But if we have that ordering, then we can sort of be in the internally aligned path. And so once we've gotten to this point where first it sort of proxy becomes perfect, and then it learns about the training process, then once that's happened, there's no additional pressure to make the model deceptive or corrigible or whatever, because once we've gotten to the point where the model has a perfect proxy, then the model is going to be doing its very best to pursue the training objective that we're trying to get it to pursue. And so there's sort of no performance gains from modifying that model to become deceptive. The only reason that you would sort of go to the deceptive equilibrium would be if there's some increase in performance, right? In this sort of high path dependence case, right? You're sort of looking at these paths. If there's some really high marginal performance improvement, then you would go there. But we've already reached an equilibrium in this case before we ever got to a point where there was a sort of reason to become deceptive. And so in this case, once we've gotten here, we're at equilibrium. There's sort of no reason for the model to change. We have this sort of internally aligned model that's doing the right thing. Okay, so this is one path. So now we need to understand how likely is this path. So I think there's sort of an issue, and the issue is this sequencing step that I was talking about. So why is this sequencing step so tricky? So I think that the really tricky thing about what I was sort of just talking about is that I'm supposing in this internally aligned case that we sort of fully understand the proxy before we sort of, we fully understand the training objective. We get this sort of perfect proxy before we sort of understand, a bunch of these facts about the world. And I think this is, the first thing that's implausible is if we're thinking about, the sort of two things that gradient descent is doing to make the model better, giving it better beliefs and giving it a better, an objective that is closer to the thing that we want. There's going to be diminishing marginal returns to, putting additional improvement in each one of those two sort of buckets, right? And so it's just, a priori seems really unlikely for you to for it to sort of be the sort of correct thing to do to allocate all of your, gains to one of those two classes and really sort of not put them in the other, right? If you have two possible things that you can improve about the model, and you're at each individual point trying to take the maximum marginal performance improvement, and there's diminishing marginal returns doing both of those two things, then you're going to be spreading out your abilities, your sort of, between the two. You're going to be doing them both simultaneously or alternating between them rather than sort of doing one and then the other. Okay, but that doesn't fully answer the question, because we still also have to understand, okay, given that gradient descent is probably going to be doing both of these things simultaneously, why would it first get to the point where it understands the training process before it sort of has a perfect proxy? And for that, it really depends on the complexity of the goal they're trying to get it to do, right? So if we're trying to get it to accomplish something that's really simple, then it might be that having a perfect proxy is really easy, right? It actually doesn't take very many steps to get to a perfect proxy. We can just get there and we get the internally aligned model. But if the thing we're trying to get to do is really complicated, if we're trying to get to do something that requires a ton of complexity, something like do what humans want to do, that requires all of this, pursue human values, whatever, something really, really complex that has all of this sort of inherent complexity, then it's going to be really difficult for the model to just sort of memorize all of that information directly. And in the same sense that we were sort of talking about at the end of the last lecture, where it's just substantially easier for once the model, given that these two processes are happening simultaneously, and you are developing a bunch of information about how to understand the world, then information is sitting there. And so it would make more sense for the model to make use of that existing circuitry, right? In the same sense, in the high path dependence case, where we're talking about really caring about these sort of which things are the biggest marginal performance improvement, given that we've already started with this other circuitry. If we're starting from a case where it's going to be improving its model of the world alongside it, then we should expect that it's going to, the thing that's going to give us the most marginal performance improvement is to make use of that existing circuitry that understands the world and has a bunch of knowledge about it. Rather than just sort of reinventing the wheel entirely and sort of just hard coding the thing that we wanted to do separately. Okay. And so the basic case here is, understanding the world is something that is just generally really valuable in lots of cases. It's something that is going to have a lot of, sort of reasons to increase it in many, many different scenarios. And getting a better and better proxy is something that is maybe, more difficult. It's something that, has potentially more diminishing marginal returns, is something that maybe requires more complexity, is something that can be done maybe more easily, given that you already have a bunch of understanding of the world in terms of that understanding of the world, rather than sort of trying to implement it separately. And so we're sort of worried that this sequencing might fail, that we might get the opposite sequencing, that instead, understanding the world, and understanding the world sufficiently to understand the training process could happen before we get the sort of perfect proxy. Okay, question.
What do you think will happen if the proxy is sort of good enough for like not perfect, but like decently close to what we want, and the model will learns about the training process at that point? Do you think it'll like keep caring about the proxy goals, like, oh, I really want to do this thing that is not exactly what we want, but like very close to what we want? Or do you think it will like stop caring about that at all?
Yes, I think this is sort of part of the key concern here, is that the proxy could get really, really close. But as long as the proxy isn't exactly the thing that we want, then there's still some pressure to be deceptive, right? So as long as the proxy hasn't matched up exactly on the desired thing, then there's some gains for that model from pretending to do the desired thing and then waiting and then eventually doing the slight difference, right? And that's sort of dangerous because if that slight difference is something that we really care about, that could be very problematic. And so this is sort of one of the other things that's happening here, right? Is that this sort of perfect proxy standard can be very rigorous, right? It depends obviously on how hard it is, the objective that we're actually trying to get it to accomplish. But if we're trying to get it to do something very, very complex, having a perfect proxy is a very, very high standard. And given that both of these sort of two things, improving the world model and improving the proxy, are happening simultaneously, that really high standard might be something that's really, really hard to meet before you have understood the training process sufficiently. Yeah, question.
How sure are we about that part that a little difference in the objective function causes huge tragedy after deployed? Like, how confident are we in that?
Yeah, well, I think it really depends on the difference, right? So some small differences we might be totally fine with, and some small differences might be catastrophic, right? So it really depends on what is the metric? I mean, the metric is just, is that difference about a thing that we really care about, right? So if it has a really small difference in what it's doing that is directly around something that is extremely important to us, then we're going to be really sad. And if that small difference is something that is totally irrelevant to anything that we humans care about, then we don't care, right? So is a small difference dangerous? Well, maybe. It's not like in general dangerous or in general not dangerous. It depends on what the difference is, right? Okay. Okay, great. So corrigible alignment is the second path. This is the Martin Luther path, and we want to understand how likely is the corrigible path. So again, we're going to start with this proxy aligned model, right? We're going to start with this case where it has some proxy. The proxies aren't really great. But now we're going to imagine that we're sort of going to accept the argument we were talking about previously about, okay, it seems really weird in some cases to sort of get this perfect proxy before you've understood the training process. So what if instead we imagine these two things are happening jointly, right? It is jointly improving the model's understanding of the world and improving its proxy. And then we're going to imagine, well, at some point the model is going to learn from its input data, from understanding the world. In the process of understanding the world, the model is eventually going to learn a bunch of facts about the training process. And here we're going to imagine that happens before the model's proxy sort of becomes perfect. The opposite sequencing from the last time. And then, given that sort of opposite sequencing happens, then what we're going to imagine happens is that the proxy gets replaced with a sort of pointer to what it is that we're trying to get the model to do in the model's understanding of the world, right? The model now understands, has a bunch of facts and information about what the humans or what the training process is trying to get it to do, and so gradient descent can just get rid of the existing bad proxy and replace it with this much better proxy that is, you have this understanding of in your understanding of the world somewhere. So just do that thing, right? Do that thing that you already understand, and that could be substantially simpler and substantially better, right? Because if we're in this situation where your sort of world model, has a better understanding of what it is that you're trying to get the model to do than the proxy does, then there's going to be performance gains from ripping out that proxy and replacing it with the thing that is sort of pointing to the understanding of the world. We can sort of think about this as if the sequencing happens in this direction, opposite of the previous one, there's a sort of performance overhang where so long as the model still has its sort of bad, imperfect proxy, there are performance gains to be had from replacing that proxy with the model's understanding of what we want it to do that exists in the world model, right? The model sort of, in some sense, in this case, knows what it is that we want it to do, right? It knows a bunch of facts about the training process, knows a bunch of facts about what it is that we're trying to get it to do. But those facts sort of haven't connected to the model's actual desire to act because it just has some proxies that are still there that that it's using to determine what it does. And so that sort of creates this overhang where it theoretically should be able to do better than it actually is because it does have the knowledge of what it is that we want it to do, but it's not making use of it effectively. And so what sort of ripping out the proxy and replacing it just with like a pointer to its understanding of the world, understanding of what we want it to do, it sort of resolves that overhang and sort of gets into a position where now the model is actually making use of that knowledge that it has effectively. And so that's sort of a substantial performance improvement because it solves all of these examples where the model actually did understand what we really wanted to do, but didn't actually correctly act on that in training. Okay, and then again, once we reach this point, we're at a similar sort of equilibrium previously. There's no additional reason to change the model in any direction because it sort of fully understands what we want and is doing the right thing in training in every case. Okay, great. So this is sort of another path. And so now we need to ask, again, how likely is this path? And I again have a concern. So here's my concern here. So we talked previously, right, in the first, in the internal alignment case, about the difficulty of getting a proxy, right, that was perfect, right? The difficulty of getting a proxy that really directly captured everything that we cared about. Well, the same sorts of difficulties also arise in getting a good pointer. So you can think about it like this, right? So, Martin Luther, right, needs to figure out, what it is that God wants to do, and so he's going to do that by like reading, a Bible. But, which Bible, right? Like, how should he read it? How should he interpret it, right? These are all really, really tricky, difficult questions that, many different sorts of Martin Luthers, different people that have tried to interpret the Bible, have disagreed on. And so if you want to make sure that in every individual training example, the sort of correlative aligned model actually gets it right every time, it's not enough to just sort of point to that understanding of the world, right? You can have a perfect understanding of exactly how, what the Bible says and what's going on in the world, but not have a perfect, not be able to understand which of the pieces and which of the things in the world are the ones that we actually care about, right? You have to be able to, understand if you're trying to like follow human instructions that it's not, follow the instructions of, whoever is typing at the keyboard, but it's like following the instructions of the human, right? There's all of these sorts of, tricky difficulties in actually being able to understand, okay, of all of these facts that exist in the world, which are the ones that actually correspond to the thing that, you're trying to get me to do, right? And that isn't a fact about the world as much as it's just a thing that that's a fact about what we're trying to get to do, right? It's just a basic structural thing, right? You can understand all of the facts about the world, but it's not clear which of those facts necessarily is the one that we want it to be caring about, right? And that takes some additional sort of, tuning to find the correct way of interpreting which thing in the world it is that we want the model to be doing. And so in the same way that sort of, getting a better and better proxy is this sort of long and arduous path where, there's sort of diminishing marginal improvement to getting a better and better proxy at each, step along the way. There's also diminishing marginal improvement to getting a better and better pointer, right? So, eventually, yes, if it has, a perfect pointer and understand exactly what we're trying to get it to do, it's going to have perfect performance. In the same way that eventually, if it has a perfect proxy, it understands exactly what we're trying to get to do. But getting to either of those situations still requires this sort of long and arduous path of incremental improvements where, the pointer gets a little bit better, the proxy gets a little bit better, and eventually, they sort of match up with what we're trying to get them to do. But that long and arduous path can be one that is not necessarily super favored by gradient descent. It's one that in this high path dependence view can take a bunch of steps and can be a bunch of steps that have smaller and smaller performance improvements as we're going along. And so in that case, we're sort of concerned here. An important thing, right, to point out though is that we're really relying on this fact that the thing we're trying to get to do is really complex and difficult to learn, and it's difficult to point to. But that's going to be true in many cases where we're trying to get our models to do really complex, difficult, complicated, important tasks. And so when we're in that case, we're sort of dealing with this problem that, well, there's just going to be a bunch of things that we have to get the model to, get exactly correct if it's going to be able to sort of do exactly the thing we want. And that's sort of still the case in either the corrigible or the sort of internally aligned case. Okay. Okay, so we have path number 3, which is deceptive alignment. So how likely is a deceptively aligned path? So the deceptively aligned path starts out very similarly to the corrigible path. We're going to imagine that we start with a proxy aligned model, and then we're going to imagine that similarly to the corrigibly aligned case, we have the sequencing in the corrigible direction, where first we learn the understanding of the training process before we have learned the sort of correct, perfect proxy. Okay. And then once that's happened, we sort of again have this overhang, right? This sort of overhang that we were talking about in the corrigible case, where there is sort of performance improvement lying on the ground, where the model theoretically knows, in terms of its knowledge about the world, a bunch more facts about the training process, a bunch more facts about what we're trying to get it to do than it's actually making use of in terms of it, how it's actually taking its actions, because it's just operating on some proxy. And there's something has to happen, right? Gradient descent is going to do something to resolve that overhang. And in the corrigibly aligned case, the way that overhang was resolved was it ripped out the proxy and replaced it with this pointer to understanding these facts about the world. But in the deceptively aligned case, there's something different that gradient descent can do that resolves the overhang that also resolves the overhang. So what can gradient descent do? Well, it can take the existing proxy, whatever it is, and make it into some sort of long-term goal, right? So whatever the existing proxy was that it had, if that proxy becomes a long-term goal, then given that the model has an understanding of the training process and understands how it works and what we're trying to get to do, if it has some long-term goal that is different than the goal that we are actually trying to get to do, then it has an incentive to be deceptive, right? Now suddenly it has a reason to try to play along so that eventually it can do its long-term goal that it really wants. Okay, and so in the deceptive case, there's an alternative modification available to gradient descent. The gradient descent can change the model in a different way than the corrigible case that also resolves this overhang, right? In both cases, in the deceptively aligned case, it had more information about the world that it could be using to take good actions that it wasn't, right? Because it sort of had this bad proxy. And the corrigibly aligned case, what happens is it makes use of that information via pointer. In the deceptively aligned case, what happens is it makes use of that information via instrumental reasoning, right? It just reasons. It's like, well, to be able to get whatever this long-term goal is, the best thing for me to do is to do what this training process wants. And so I'm going to do exactly what the training process desires. And a really, really important point here is that this instrumental reasoning doesn't go through the same problem that we were talking about earlier about this sort of difficult path, incremental path, because the deceptively aligned model doesn't actually need to know all of these sorts of same facts that the corrigibly aligned model does about exactly how what thing to point to, because the deceptively aligned model just figures it out based on reasoning through. Well, I'm going to just do whatever thing in fact results in me doing the best, eventually being able to survive this training process, right? And doing that reasoning lets it figure out what are the things that it should be doing, right? Because the actual things we wanted to get to do in training are, doing those things are going to be the things that most let it survive training and do whatever it wants later. And so, we could imagine a case where you have a corrigibly aligned model, and the pointer that the corrigibly aligned model has is to whatever things let you survive the training process so eventually you can do some evil thing. And that would work, right? But that's the deceptively aligned model, right? That is what the deceptively aligned model is doing. It's sort of like a corrigibly aligned model where it has some pointer that describes exactly what it is that in the world model that it should be paying attention to. But the way that pointer is implemented in the deceptively aligned model is by doing this instrumental reasoning, by figuring out, okay, look at your understanding of the world, and based on your understanding of the world, figure out which things you should pay attention to, such that if you paid attention to those things, you would be the most likely to be able to get some long-term goal eventually in the real world. And that's a really efficient and effective way to implement a pointer, right? And so in the same way we were talking about in the corrigibly aligned case, where there's this really difficult long path to be able to get a sort of pointer that sort of actually is able to accomplish the correct thing. The deceptively aligned case, it can get there very quickly, right? All it has to do is get some long-term goal, have some long-term goal that you eventually care about, and then all of this sort of performance overhang is immediately resolved. Because to the extent that the model had already the information about what it was that the training process actually wanted to do, as soon as it has the objective of, okay, playing along in the training process, it's immediately going to be able to capture all of that performance. Yeah, question?
I'm not sure it's well formed yet, but basically, there doesn't seem to be much of a difference in complexity. I'm confused why you say that this is more efficient, like an easier pointer to learn. In most cases, you need to learn from a pointer to like do the thing that the training process wants you to do. In the deceptive case, there is an additional reasoning step for instrumental reasons. So it just seems like the deceptive case is harder to get to.
Yes, this is a really good question. So let's try to break this down. So I think that one thing that is sort of really tricky here is distinguishing between two sort of notions of complexity. So we talked, so one notion of complexity is, what things have to be in the algorithm, right? What things sort of have to be encoded in the weights? What are the sort of structural properties of the algorithm that need to be specified for the model to be able to do a good job? And then there's another thing, which is, what things does the model have to figure out? Right? What things does the model have to figure out every time you run it, right? When you run the model and when it does a bunch of thinking, what are the things it has to discover in that thinking? And here we're imagining, well, it doesn't matter that much, what happens in terms of the, in some sense, all of these models eventually are going to have to discover the same things in thinking, right? Because they all fully understand what we want, right? And so to be able to fully understand what we want, when you run them, they eventually have to get to the point where they have the exact same understanding of exactly what it is that we want. What's different is the way that they do it, right? What's different is the, what has to be encoded in the actual algorithm that results in them having an understanding of what it is that we're trying to get them to do, right? And so the difference here is not that they don't have the same understanding. Eventually, every time you run them, they're going to have the same understanding, because they didn't have the same understanding, they wouldn't be able to do a good job. But they get there in different ways, right? The internally aligned model gets to that understanding by having it 100% fully hard-coded. It just loads it straight up from the weights, right? The coercively aligned model, it gets it by having some pointer, some function that takes in the world and outputs, takes in its understanding of the world, a bunch of facts about the world, and outputs what is the thing that I should be, trying to do in this case. The deceptively aligned model, like the coercively aligned model, also has this like function, right? But its function is different, right? In the coercively aligned model, we're sort of, requiring that function to be a function that actually is correct, right? It is the correct function. It's the one that actually does the right thing, that actually takes in understanding of the world and outputs the correct thing that we humans would actually want it to do in that case. But the deceptively aligned case doesn't have to implement the correct function. It can implement an incorrect function. It can implement the function that is just, do simple instrumental reasoning, right? Start from the premise, I want to accomplish some long-term goal, and then figure out which of these facts, based on that premise, which of these facts would be most relevant to pay attention to accomplish that goal. And so the deceptively aligned model can have a substantially simpler function there that does that transformation. From facts about the world to each individual runtime, what is the thing that I should actually be paying attention to and trying to accomplish in this individual instance based on those facts. And so that's the difference, right? Is that the way that they actually get to what is the thing they're trying to get to do is different. And in the deceptively aligned case, it doesn't have to, let's think about, right, in the coercively aligned case, we were talking about all of these various facts about, like, should I pay attention to the human in the chair? Should I pay attention to, the human, whoever's typing at the computer, or like the actual human? Those facts have to be hard-coded somewhere, right? The correct function has to just directly load up. I'm supposed to look for, the actual human. I'm not supposed to just look for, whoever's on the computer, because that's the actual correct implementation of the function. But the deceptive line model doesn't have to hard code those facts, right? All the deceptive line model has to do is have a good general purpose reasoning system that says, based on these facts, what is the actual best thing for me to do to get the most, do the best on my long-term objective? And so it just does that computation, and that's how it implements that function. And so because of that, it doesn't have to have all of these sort of difficult, incremental, things that it has to learn. It just, runs this basic reasoning process. And it should already have the reasoning process, right? Like it doesn't need to implement some new reasoning process, right? We're imagining it's already a proxy-aligned model. It already has good reasoning processes that are sort of generically there in the model. And so it can just make use of the existing reasoning processes and just use them for the goal of trying to accomplish some long-term goal. Yeah, questions?
Okay, I think this last sentence is the one that's not clear for me. So let's suppose that this sort of AGI is something that we develop as a scientist AI, like the lab that develops it, its goal is to have them develop better cancer cures and chips and whatever. I can imagine it already has some proxy goal, which is sort of what we want. It's already pretty good at its job because it really understands biology really well. But I imagine that it's plausible that from its bird model, the kind of steps that are needed to follow a goal and deceive people by following the goal, these kind of things are not yet built in. So building this up seems to be approximately as hard as modifying its pointer to a better pointer.
I think that's a really good point. I think that, and in fact, probably, I don't know if we'll get to it, but we might potentially much later talk about proposals that sort of try to leverage that intuition. I think that's basically correct. That in fact, if you are training an environment where being able to do this sort of instrumental reasoning is just not helpful for performance, then this path looks way less good. Because now gradient descent has to actually do the work of hard coding in all of the instrumental reasoning capabilities. Rather than just being able to make use of the existing circuitry, right? And in that case, yeah, I think I agree that this path, at least in the high path dependence case, looks worse. It doesn't seem like it outperforms. I'm mostly imagining a situation, at least here for our purposes right now, where you're trying to get to do something very complex and very difficult. Some very general tasks we wanted to do, all the things that humans want or whatever. Because we're sort of just imagining this like default case where we just like throw machine learning at all of the problems that we wanted to be able to solve. I agree that there may be things that we could do to try to escape that, and I think that is one of the things that we could do is try to just focus on situations where that sort of instrumental reasoning capability is not relevant. I think that the issue with that sort of approach though is that people do want AIs to be able to do tasks where instrumental reasoning is important, right? And so eventually you have to be able to confront that fact, right? We have to, as a society, deal with the fact that there are people who want AIs to do things that require instrumental reasoning, and we don't want them doing that to be catastrophic.
Okay, and what do you think how specific this instrumental reasoning should be? So if let's say that they are developing an AI whose goal is to build a good factory. If it involves lots of instruments, it needs to have some sorts of instrumental reasoning. Because building a factory has lots of instrumental steps. First, you need to buy concrete and whatever. But still, I can imagine that the part that you are negotiating with somebody who you need to deceive, these circuitry would not exist at the beginning at all, and again, it would need to build it from the ground up, and maybe it's not worth it.
Yeah, I think it's very unclear. There's definitely going to be some gray areas where like it might have some instrumental circuitry, but not maybe all the instrumental circuitry it needs. And in that case, it's going to be somewhere in the middle, right? It's going to be like maybe this path looks okay, but it looks like less good than the case where it already had all the circuitry. So yeah, there's going to be a bunch of gray areas where if it has like no instrumental circuitry, by default it doesn't need to solve the task at all, then this path looks the worst. And if it's solving a task where the instrumental circuitry is just always necessary to solve the task regardless, then this path's going to look the best. Yeah, question.
Just to be clear, is the effectiveness difference does this come from the fact that for a corrigible model it needs to update the pointer, like a very complicated pointer, through SGD, while the deceptively aligned model needs to only update the instrumental goal through SGD, and you're saying that the deceptively aligned model would do further reasoning on top of that in an OR pass. Is that where the effectiveness difference comes from?
I think that is basically right. Yeah, we're sort of distinguishing between what things does it learn via like hard coded in the weights, and what things does it figure out that like end up appearing right in the activations, right? What things does it figure out at inference time, It doesn't necessarily have to be like, oh, every single time it does the reasoning. If you have a model that can like cache beliefs and like store information, maybe it has a retrieval database or something, then it's not necessary that like every single time you run it, it has to rerun the computation. But yeah, we're imagining that essentially the information there about like, okay, this is the thing that I should be doing in this case was mostly generated by the model rather than gradient descent, right? Gradient descent just produced the long-term goal. Yeah, question.
It seems like both of these paths involve like model learning about its proxies or its goals. At the same time, it's acquiring its knowledge. So, but like I feel like in current ML systems or in current systems like ChatGPT or GPT-3 with then plus RLHF, like GPT-3 is just like acquiring the model's understanding of the world, and then RLHF then like gets or points to like gets a model to point to a specific goal that it's already learned. So in this case, which would be selected, the instrumental goals or the actual goal?
Yeah, so that is the case where like the internally aligned path is like the least likely, right? Because in the case where you're just sort of trying to put the goal into the end and you start with pure knowledge learning, you're not going to get this instrumental path where it learns the goal first, right? Now, whether you get the corrigibly aligned path, the deceptively aligned path, or something else, it's not these three paths are not exhaustive, right? And again, we'll talk later about other sorts of things that you might get when you're trying to train this sort of predictive, like a language model. But at the very least, yeah, I think that the thing you're saying is at least some evidence that the internally aligned path specifically is really unlikely in the case of doing this sort of fine-tuning regime. Okay, yeah, more question.
I'm sorry, I'm not quite sure why the internally aligned path wouldn't be unlikely in this case, because I feel like that would have at least the same probability as the deceptive or the corrigible aligned path in this case, because like you just need to choose any goal, right? And if like instrumental goals and the terminal goal is like equally likely to be selected in this case, since the model has a knowledge, why wouldn't the internally aligned path be equally likely?
Yeah, so the problem is that the internally aligned path sort of hard codes the goal, right? Rather than having it be coded in terms of the model's existing knowledge. But if the model starts with a ton of existing knowledge, including a bunch of knowledge about exactly what we're trying to get to do, then it's going to be a way shorter path and substantially better to just make use of that existing knowledge somehow, right? Because it's already there, right? And so it's not going to want to re-implement it in some hard-coded proxy. And so in that sense, it's going to be substantially more favored when you're starting with that knowledge already existing to go down either the corrigible or the deceptive path. Okay, so okay, great. Yeah, so we've been talking about like how likely is the deceptively aligned path. The basic case is that turning your existing proxy into a long-term goal is a relatively simple modification, and importantly, it's a modification that doesn't have this like really long path. It's a relatively straightforward modification. Once you do it, once you sort of go to a long-term goal, you capture all of the gains from that overhang, right? It doesn't have to like keep improving the long-term goal to be more and more long-term, right? Once you get the long-term goal, then as soon as you have a long-term goal, it's going to do all the instrumental reasoning necessary to figure out exactly what the thing is that it should be doing to get the most performance in training. And so it doesn't have this long and arduous path in the same way that we've been talking about earlier. It has this single thing that it has to do, and once that thing happens, it gets all of the sort of performance from the overhang. And so because of that, this is sort of a path that we might expect to be favored in this sort of high path dependence case. Now, there's a bunch of assumptions, right? So one important thing, right, is that we're doing something that's really complex goal that like we were talking about. Also, we're doing something where there already exists good instrumental reasoning circuitry. But if we're in that setting, then this path seems very favorable. Okay, so that's the high path dependence case. Now we're going to shift gears. And we're going to talk about the low path dependence case. So we want to redo the whole analysis that we just did, but under a different view of the inductive biases, right? A different way of thinking about what it is that determines which algorithm we get. Okay, so again, we're going to be assuming the model has to fully understand what we want in terms of what model classes we're looking at. We're going to be imagining, but then to be able to distinguish between these model classes, we have to look at what are the things that are going to matter in terms of properties of an algorithm that you might look that the low path dependent sort of inductive biases might be looking for. What does it mean for an algorithm to be structurally simple? And in particular, we're going to isolate two things. And I sort of alluded to these earlier, where thing number one is simplicity and number two is speed. So what is the difference between these two things and what do they really mean? So it's a little bit tricky what they mean. So I'm going to try to unpack them. So simplicity is how complex is it to specify the algorithm in the weights, right? If I were to write down, a Python program that ran exactly the algorithm that my, was being implemented by my model, how many lines would that program take, right? We can think about this also, right? If we think about, how complex is the algorithm of, right? If we're thinking about something like the wheels, windows on top of wheels detector, how complex is that basic structure, right? First you have to have a window detector. You need some window detection function and then some wheel detection function, and then you need to write the, combine these two function, right? And so we're sort of trying to understand how complex is that circuitry, right? How complex, is the description of the circuitry that the model has to implement, right? The thing that this doesn't capture, right? So the thing this is explicitly not capturing is the complexity of actually running that circuitry, right? It's only the sort of simplicity captures the complexity of describing the circuitry, and then speed captures the difficulty of running that circuitry. Now, an important thing to point out is that in many realistic architectures, it is in fact the case that they actually all take the same finite amount of time to complete. And so we need to be really clear here that what we're talking about is not the literal algorithm that is implemented by the weight matrices, by your actual neural network. We're talking about is the sort of the structurally simple algorithm that is sort of behind it, right? What is the algorithm of the core thing that it's actually doing? It's like look for windows, look for wheels, combine them, right? And we want to understand for that core thing that it's doing, how much computation does that algorithm take, and how difficult is it to describe? So some ways of thinking about why these two things matter, right? So why does it matter? How complex is it to describe the algorithm? Well, it matters how complex is it to describe because that matters. That affects things like how large is the basin going to be? Because the more complex it is to describe, the more parameters it's going to take to be able to describe it. And so it's not going to be the case that there's going to be a bunch of different possible parameterizations which all correspond to the same function. But if it's very simple to describe, then there may be many parameterizations which all correspond to the effectively same simple structural function, right? So simplicity matters. And speed also matters. So why does speed matter? Well, it's a little bit trickier. So one way to think about this is if we're thinking about the space of all possible algorithms that one could have in theory. Well, just to start with, only some of those algorithms are actually implementable in a neural network, right? Because it actually is a finite function, and it can only implement so much computation. And so we should expect that algorithms which effectively take less computation will also be more likely for us to find, given that we don't know exactly which ones are going to be included in the space of which, at any given point, is our network large enough to be able to implement it? But if it's implementable, via a smaller network, then, it might be more likely that we'll find it earlier. Similarly, if the model, if it's an algorithm that takes a bunch of computation, and there's another model that accomplishes the exact same thing but takes less computation, then that means there's sort of extra, computation. There's sort of extra computation available to sort of do other things, like spend extra, computation, in slightly improving its performance in various ways. And so, both of these two things matter to some extent in terms of understanding, how likely is a particular algorithm. Now, they're definitely not the only things that matter, even in a low path dependence case, where we're imagining that the only thing that matters are these sorts of global structural properties of the algorithm. Even in that case, there's almost certainly other global structural properties that matter too. But these are at least two that do seem like they will play a role and are ones that we can sort of analyze. And so we'll be imagining that these are the main two that we're sort of going to be looking at. Yeah, question before we go.
Could speed affect simplicity as well? Like, let's say I have a 10-layer neural network, and I have two algorithms. One requires 10 successive computations, so the only way to do it is to be in all 10 networks, in all 10 layers, and the other has 2 layers. So that means there's 9 different ways it can actually be instantiated. It can go from layers 1 to 2, all the way through to layers 9 to 10. So would faster algorithms also be simpler to specify in some way?
Yeah, I think that is a really interesting point. I think that it seems at least plausible. I don't know, in fact, how it works out in terms of, how these things interact. I definitely agree that, they're certainly going to interact to some extent. And there are various models of trying to understand how they interact. I think one model of sort of trying to understand how these things interact that is, I think is sort of reasonable is like a circuit prior model, where you sort of try to understand, if we think about, algorithms as being described by the Boolean circuits that are necessary to implement them, then, we can think about the inductive biases as selecting the algorithm which takes the fewest number of Boolean circuits. And that, in some sense, sort of is capturing the thing you're saying, where it's sort of a mix between speed and simplicity, where the sort of faster models also take fewer circuits to implement. A lot of those sorts of priors, though, are harder to understand. They're harder to sort of figure out, would the deceptively aligned or the non-deceptively aligned actually do better? And so we're going to imagine that we're sort of going to be thinking about a case where, we're just going to be looking at those two specific things. Question?
Yeah, I didn't want to ask a question, just to make comment on the previous question. An example of like the case where there would be difference between simplicity and speed is, imagine if in every layer you only need like one neuron for this algorithm, but you do need nonlinearity, so you do need the values, so you do need like 10 consecutive layers, but you need only one neuron in each. So this algorithm would be simple to implement, very few weights are needed, but it will be like long because so many steps are needed.
Yeah, it's a good example. Yeah. So we care about both of these things. They're definitely going to matter to some extent. We don't know exactly like what the mix is of them, and how things play out in terms of, which one of these is most important. But we're just going to look at both, and we're going to try and understand under each one of these regimes how well do these different model classes perform. Okay, so we're going to start with simplicity, and I'm going to start with a really simple argument for trying to start getting our hands on simplicity. I think one way to sort of think about simplicity is just how many algorithms are there, how many possible ways are there of implementing a particular algorithm, right? So we've been talking about this as this relationship between simplicity and basin size, right? Where the more ways there are in implementing the same algorithm, the larger the basin is. And so we can sort of understand, well, okay, effectively how many different sorts of algorithms are there which fall into each one of these model classes. And in the same way that the sort of number of possible weights that implement the same algorithm affects the simplicity of that algorithm, the number of algorithms which fall into the same model class affects the overall simplicity of that model class. And so we're going to start with the counting argument, right? How many algorithms are there that fall into each one of these classes of algorithms? So how many Jesus Christ are there, right? How many internally aligned models are there? Or at least how many algorithms are there, effectively different algorithms which implement the Jesus Christ model? I think the answer here is basically one, right? There is only one way to sort of hard code exactly what it is that we want the model to be doing, right? Any sort of difference in that, would be a different model, right? We would no longer be the Jesus Christ. It wouldn't be doing the correct thing. Okay, but how many, Martin Luthers are there? Well, there's a bunch of different ways of looking at the Bible that are all the same, right? You can have a bunch of different ways of thinking about and understanding exactly what it is they're trying to get to do that all converge on the same thing. Now we talked previously about that can be difficult, right? It can be difficult to get the exact correct pointer, but there's still multiple of them, right? There are still understanding exactly how to read the Bible plus any one individual Bible that exists in the world will all yield the same results as long as they have the same contents. And so it's still the case that there are multiple different Luthers. There are still multiple different ways of pointing to the thing that we want. And similarly, if we think about Pascals, well, there's even more sort of Pascals, because any long-term goal that you could possibly have would correspond to a Pascal model, because any long-term goal will result in the thing being deceptive. As long as it has something that it wants to accomplish eventually in the world, then it's going to want to play along and be deceptive for the purpose of doing so. And so just based on sort of initial analysis, it seems like there's the largest number of models occupy the Pascal model class, the deceptively aligned model class. Okay, we can sort of dig in a little bit more if we sort of try to think about what's going on here, right? That's causing this sort of Pascals to be sort of more numerous. Well, we can think about sort of the simplicity and the complexity of an individual model as being described by the complexity of sort of three pieces, right? We have the world model, its understanding of the world. We have its optimization procedure, its ability to do instrumental reasoning, to do all of these sorts of tasks. And then we have the Mace objective, right? Whatever it is that it's trying to use that reasoning to accomplish. We talked previously about cases where the optimization procedure or the world model can be different, and that can really affect which thing you end up with. In this case, if we're imagining a case where we're really trying to get it to do some really complex task that requires general purpose instrumental reasoning, and it requires it to basically know all various facts about the world, then all three of these model classes should have, in that specific case, essentially identical world models and optimization procedures. They should have to be able to do the same reasoning. They should have to be able to have the same knowledge. And so then in that case, the only thing that will differ between them is the complexity of the remaining thing, which is what they're trying to do. And in that case, the complexity of what they're trying to get to do, well, if we think about that, we can sort of approximate it as, well, what is the simplest model, the simplest objective, which falls into each one of these classes? is going to be, what is the simplest MACE objective, right? That falls into each one of these classes. We can compare the complexity of the simplest one as another sort of metric of trying to understand how simple are these different classes, right? So our first metric up above was just how many different algorithms are there that fall into that model class, and that sort of can help us get some understanding of complexity. And then the second thing we're going to look at here is, for each individual model, what is the simplest model in each class, and how do those simplest models compare? And to do that, if we're imagining they have the same world model and the same optimization procedure, then the simplest model in each class is just a question of what is the simplest MESA objective in each different class. And so in the internally aligned case, well, the simplest MESA objective is going to be a full specification of whatever it is we're trying to get to do. And so, well, the complexity of that is going to depend on how hard it is, how complex it is, the thing we're actually trying to get to do. But if we're trying to get to do something really complex, then this is going to be really complex. Similarly, with the cordially aligned case, well, what is the simplest cordially aligned MESA objective? Well, it's whatever the simplest specification is of how to point to the desired objective, right? And like we were talking about previously, if the thing we're trying to get to do is very complex, this can be very complex. It requires hard coding a bunch of information about exactly which things in the world are the ones that we want the model to be paying attention to. And then for deceptive aligned, well, what is the simplest deceptive aligned MESA objective? Well, it's whatever the absolute simplest possible long-term objective is, right? Make paper clips or whatever, is the sort of thing that we get here, right? Like anything that eventually you want to accomplish in the world that is long-term, that you care about the long-term consequences, whatever the simplest possible thing is to implement is the simplest possible deceptively aligned objective. Now that doesn't mean, right? An important thing to point out here is it doesn't mean that you would literally get the simplest thing in each case, right? We're not saying the simplest thing is actually the most likely. We're saying that looking at what the simplest thing is in each class can give us a sense of how simple the overall class is, in the same way that looking at the number of things in the class can give us a sense of the overall simplicity of that class, right? And so we're saying, well, the fact that the simplest thing in this class is really simple, it's just like the absolute simplest thing that you could care about anything in the long term, is indication that this overall model class is very simple. In the same way that the fact that there's so many different models that fit into the class is also a similar indication. Yeah, question?
To link it to the previous discussion of the difference between effectiveness of corrigible and deceptively aligned, the efficiency of the processes, you're saying this is the simplest thing to do, or this is the only thing that we have to do is point to the long-term objective for the deceptive case, because we do not need to encode to make a pointer to the training objective in the weights, correct? Because the model thinks about that, could think about that in the activations.
That's exactly correct. Yes, we're imagining that the deceptively aligned model sort of figures out the thing we're trying to get to do in the activations. It figures it out, on its own, rather than sort of it being hard-coded in the algorithm itself. And so because of that, the only thing that we need hard-coded in the MESA objective part is just some long-term objective. And then the sort of world model and optimization procedure take care of figuring out what it is that would actually do a good job on that objective. Okay, so this is the simplicity. I think that editorializing a little bit, I think my sense is that this is the strongest case for deceptive alignment of any of the various different things that we're looking at. If you were just looking at purely simplicity, then I think the case for deceptive alignment is very strong. I think it's stronger than in the high path dependence case, or in general in the low path dependence case, because as we'll see, some of the other, the speed is much less clear. So let's look at speed. So how much computation does each one of these algorithms take? Well, I think that the most basic thing, the first thing, is that deceptively aligned model seems to be taking more computation, right? So why is that? Well, the deceptively aligned model has to do this extra step of instrumental reasoning, right? It has to go through this process of, okay, starting from the fact that I want to get some long-term objective, I then have to figure out, given that I want to do some long-term objective, what is the best way to accomplish that? And given that I'm in some training process, what is the best thing to do for accomplishing that training objective? And therefore, I should do this particular training objective, right? And that is a chain of instrumental reasoning which takes time and computation to actually be able to run, right, and figure out. And so the deceptive aligned model is doing extra steps of reasoning, extra computation that the other models are not doing. And so because of that, the deceptive aligned model seems to be the slowest in the sense that it is sort of taking the most steps of computation. Okay, and the corrigibly aligned model is sort of does less computation. I think that the difference between the corrigibly aligned and the internally aligned model is a little bit unclear here. I think there is some case to be made for why the corrigibly aligned model might be slower, because it doesn't get to just sort of like directly load up exactly what the desired thing is. It has to still follow the pointer in some sense, and so that takes some amounts of computation. But it seems like the difference between the deceptively aligned model and the others is at least is larger, where there's this like substantial extra thing the deceptively aligned model has to do, which is like reason about what a good what a deceptive model should do. What should I do if I'm trying to play along, right? That takes reasoning, and that extra reasoning adds to the overall computational cost of this algorithm. And so the deceptively aligned model sort of seems to be the worst on the speed case. Yeah, question.
So it seems like one thing that could take time is like reasoning about how you could be deceptive, but it also seems like just doing the task itself would take time. So how do you know that the amount of time that's being taken by the computations isn't just for the task? Couldn't like the deceptive model mask the fact that it's like taking extra time to the fact that like it's taking extra time to do the task itself?
Yeah, so I think this is a really interesting question. So it's totally the case that they're going to have to take a bunch of time to actually do the task itself. We're trying to factor that out and trying to understand, okay, what is the time you would have to take in addition to the thing you have to do to actually solve the task? And the thing that the deceptive aligned model has to do in addition is figure out what the task is, right? Like, oh, that it should be trying to play along in this case. Now, I agree that it could be the case that it could like find a way to hide that by like doing it in parallel or something. Another way that it could hide this is via like a retrieval database of some variety where it's able to just like store and cache its previous computation and then load it back. Those could definitely be cases where this sort of thing would get trickier. I think one thing I'll point out about the like doing it in parallel is going back to like why would we even expect that like speed bias would matter at all? Well, the reason we'd expect it to matter at all is that to the extent that it's sort of using it has like some finite amount of computation available to it. And to the extent that it's using some of that computation to do other stuff that's not directly necessary, then it's sort of wasting some amount of computation that it could be using to like try to do other things that are better for accomplishing the task. It means that it has to be implemented on maybe a slightly larger model or a slightly different type of model, and so that can sort of push you back. But again, it's very unclear, right? Like it may be the case that you have a really, really large model that theoretically has the capacity to implement any of these things, and yet you still end up implementing the simplest one or the fastest one or whatever. Or similarly, you could have a really small model, but the simplicity bias is really strong. So it's a little bit unclear exactly how this sort of ends up, but at least if we're sort of thinking about it in this very abstract sense, where we're just looking at speed complexity, right? It seems like on this sort of speed complexity case, the deceptively aligned model loses. How that actually cashes out in terms of like how these various like theoretical factors influence the actual practical inductive biases is a really difficult thing to determine. Okay, all right. So I think that this is sort of nice, right? It seems really good that speed bias sort of seems to cut against deception. But there's a bit of an issue here, which is that I think speed bias has a bit of a problem, which is that it may be sort of uncompetitive in the sense that if we try to build training processes which directly incentivize computationally fast algorithms, we may be losing a lot of what makes machine learning good in the first place. So we talked sort of at the very beginning of like, well, how do we construct machine learning processes, right? Like, why do we build these machine learning models, and how do we make them work? Well, the thing that we often will do is try to select loss landscapes, select our machine learning process to have a to bias towards very structurally simple algorithms, because we believe something like Occam's razor that structurally simple algorithms do a good job at fitting the data. And so if we are trying to modify our training process to not do that, to not be biased towards structurally simple algorithms, we run into a problem of, well, now we might not actually be able to find algorithms which do a good job at fitting the data. So going back to something we talked about in the first lecture that I think is sort of relevant here is we can think about, let's say I in fact practically tried to do this. I tried to select the model which has the following property. It is the smallest model which does a good job at fitting the data. In some sense, that's sort of an approximation of what a speed bias would be, right? It's saying we want the smallest model which fits the data well. And so this is the double descent curve from earlier. So we can say if we want the smallest model that fits the data well, then what we want to look for is we want the case where the train loss, the training performance reaches its optimal. The first point that happens as we vary model size, right? So as we slowly increase the model size, we want to stop once we reach the smallest model that has good performance. And so we can do that. The blue here corresponds to blue, and the green corresponds to green. We can do that. We can look at what happens when we reach zero train loss, and then how well does that perform on generalization tasks, right? And the answer is it's the worst point in the whole graph. If we look at how an individual model size performs on actually generalizing to downstream tasks, the worst generalization performance occurs precisely at the point where the model first reaches optimal training loss. And I think one way that you can interpret what's happening here is that, we talked about this sort of at the beginning. It's sort of, this is the point at which it's sort of forced to do the sort of fast algorithm. It's forced to just like memorize things rather than actually sort of implement the, actually structurally simple thing. And so it actually ends up doing a poor job, right? And so that's a concern because it means that we might not actually be able to get this sort of speed bias in practice while still being able to have machine learning systems which do a good job on tasks, right? In some sense, we're sort of forced to have some amount of speed bias because we don't want to waste a bunch of compute on things. But if we sort of push too hard in this direction, then we lose the thing that we wanted to get out of machine learning in the first place. Now, that might not be entirely true. So one fact here is that this speed bias is looking at the size of the entire model. But instead of looking at the size of the entire model, we can instead look at something like the depth, right? How many sequential computations are required? That's a different type of speed bias than the total amount of computation required. And if we look at the depth, then it's actually much less clear. It actually often does look like you can substantially decrease depth and still have good performance. So it's not, the jury's not entirely out here. It may still be the case that there are other things that we can do to sort of make speed bias competitive, to be able to create training processes which incentivize finding algorithms which are structurally use less computation. But it's a little bit tricky for us to actually be able to find ways to do that which actually give good algorithms. Yeah, questions?
How do you think this changes if we move to more recurrent architectures or transformers with adaptive diffuser? I mean, there were still hard coding in the preference for shorter compute time.
I think that's a really good question. So I think it does change things. So in particular, it sort of introduces what I often will call an average speed bias as opposed to sort of max speed bias. So instead of saying, we want the total amount of computation that the algorithm uses on any input to be capped at some value, we're instead saying on each individual input, we want you to use as little computation as necessary to solve that particular task. And I think that sort of average speed bias actually has reason to believe it might be more competitive and better than the max speed. And so I think there absolutely are room for potentially making use of something like that. Yeah, so an example of something that makes use of something like that would be something like chain of thought, where you sort of select for the model thinking for a smaller amount of time and still getting the right answer is sort of implementing something like an average speed bias. And so that might be a way to sort of get around this. Yeah. More questions?
This speed prior, is that something that A, someone has tried, and B, do we have the engineering capacity to actually try this as an experiment as of like now? Do we know how to actually implement a speed bias, even if we think it's a good idea to try?
Well, it really depends on what we mean by speed, right? So we can look at this graph here and can be like, well, this graph is implementing a speed bias, right? What we did was we just look at the first thing that gets zero train loss as we vary the size of the model, and then we select the thing, right? And this doesn't work in the sense that it yields bad performance. Now you could imagine doing something very similar to this, where instead of looking at total model size, you're looking at one of these other sorts of things and varying it, and then finding the first thing that does a good job. You could also just add this as a regularization term. There's lots of ways that you could try and implement it. I think the tricky thing is knowing what sort of speed bias to look for, and actually believing that speed bias would be sufficient, right? You're still going to have the simplicity bias, right? You're still going to have all these other biases. So you actually have to have some reason to believe that the speed bias that you're adding is actually going to do enough to get you to avoid the deceptively aligned model, right? And that's a really tricky thing to believe and to have any confidence in. Yeah.
But I was just thinking it would be a useful empirical experiment in order to determine the competitiveness of speed bias, ignoring whether it would actually work for the time being, which is much harder to determine empirically.
Yeah, so like I said, we have stuff like this, right? Where you can just check, the scaling laws, right, of how these sorts of things change. Yeah, I mean, checking that for lots and various different ways of setting up the training process is absolutely something I think is valuable. Yeah, question?
It's not fair to me why this graph shows speed versus simplicity. Could you give a comment about that? I would imagine that for speed would need to look at the number of layers, not the total counts of parameters which this shows.
Yeah, good point. So I think the key distinction here is that there's different types of ways of looking at speed. So there's like total computation speed and is like total amounts of computations, and then there's like max amounts of computations, right? Like depth versus total size. Those are both computation measures, right? Like the amount of total computation that it does is a measure of speed in some sense, as is the maximum amount of computation on any individual path. They're just different metrics, right? You can think about if you're thinking about like parallel computation. You can either think of the total amounts of computation done across all of your parallel threads, or you can think about, what is the time that it takes for the last thread to finish, right? And those are both metrics of computation. They're ways of thinking about how much computation did this algorithm use, but they're different metrics, right? And so this is, I agree, looking at one of those metrics. It is looking at the total computation metric, and it is not looking at the max, of any particular parallel computation. I think the thing I was saying earlier, I think the max of any particular parallel computation looks better than this. This is the one that probably looks the worst. Why? Unclear. I think that, yes, the question was why. I guess the answer would be, well, it seems like, a very, passing answer, I could say. I think that, there's something sort of right about Occam's razor going on here, where, in the real world, actual real world data and real world patterns are, more distributed according to something like a average, speed bias or a, max parallel computation bias rather than a total computation bias. Why is that? It's tricky to understand. It goes through a bunch of facts about how does the world actually work, and why is it the case that particular patterns exist in the world and other patterns don't. It's sort of a really thorny philosophical question in some sense about what makes certain hypotheses more likely to fit real world data than other hypotheses. But it sort of has to in some sense go through that. Okay, so summing up, what we've talked about today. So overall, I think my takeaway is that it seems like both low and high path dependent scenarios, seem to be in a state where gradient descent is going to want to push your model to be deceptive. Now, this relies on a bunch of assumptions. We're sort of thinking about we're in a case where we're training on some really complex thing. We're trying to get it to do some really complex task. And we're in a case where we sort of have to push to really large models to be able to solve this problem. But it seems to me like there's going to be incentives that are pushing towards the deceptively aligned model in both of these cases, or at least a reasonable probability in each case of the deceptively aligned model being favored. And that sort of seems to suggest that we're going to have to create some intervention, right? Something needs to happen. I sort of mentioned this previously, right? If this is the default scenario, right? If machine learning by default, if we just sort of run it on some complex task, it gives us something, something like this, right? There's biases pushing us in the different directions. There's some reason to believe the inductive biases would yield deceptive aligned models, some reason to believe they wouldn't. Overall, it seems like the deceptive aligned models are doing pretty well. They have a lot going for them on in both sorts of stories. And so we probably need to introduce some intervention, at least if we want to be confident that we're not going to get deceptive aligned models. We need to introduce some intervention that changes those inductive biases, some intervention that changes the way that our training process works to incentivize it to not produce the deceptive aligned model. There could be lots of things like this. We talked about transparency, interpretability. Some way of looking at the model and rejecting it if it's not doing the thing we want. Some way of changing the biases, more towards speed rather than simplicity. There are lots of things that we might be able to do. Maybe just trying to train it on a really simple objective, or in an environment where it doesn't need to do lots of instrumental reasoning. Right? There's lots of things that we can imagine changing about this default scenario that might help. But we have to do something because it seems that by default, deception is reasonably likely to be favored as the sort of best algorithm according to these inductive biases in both these scenarios potentially. Okay. So an important thing I want to point out is, we can think about this as sort of the alignment gap, right? There is some difference between the size of the basin for the good models and the size of the basin for the deceptively aligned models, right? And if we think by default, there is some chance the deceptively aligned models are going to occupy a larger basin, they're going to be more likely for us to find in training, then we need to create some intervention that changes that, right? That provides additional sort of bits of optimization, additional pressure towards the good models over the deceptively aligned models. So how much how much evidence would we have to sort of condition this prior on, where the prior is over what sorts of models we get by default until we end up in a situation where we're going to get the models that we want. How much additional sort of change do we have to make to our training process before it puts us in a situation where we get the desired models? And this gap matters a lot, right? The difference in size of these basins, right? The difference in how likely you are to get each one by default is extremely important, right? If you're in a setting where there's a massive difference in the default basin size and the default likelihood of finding one or the other, then you have to sort of make some really big, massive structural change to your machine learning process. Whereas if it's only a small difference, then you can get away with much smaller changes to the machine learning process to change, to try to escape the sort of deceptively aligned models. I'm not going to take some really strong stance on exactly how large I think the gap is or where I think it is. But this is sort of, I think, a good frame to be thinking about, what we're sort of going to be trying to accomplish is, how do we end up in some situation where we can provide some intervention that changes the, default path of what sort of algorithm you're going to get to not select for deceptive alignment. Yeah, and so that's the talk. So, we're going to be talking next time sort of about, a bunch more sort of about how do we start approaching solutions to this problem. But this is at least hopefully, trying to wrap up deceptive alignment, give us a really good grounded understanding of this very specific, failure mode that is, we're very concerned about, this, deception case. All right, we'll do some final questions.
How does this relate to like the picture of like meta learning, or where meta learning you're basically learning or an optimizer and you're learning the inductive biases to put into like another algorithm. So, and I guess it's also related to your work on like conditioning generative models. So, is the optimizer that you learn going to be like, is it possible for it to have like a different like mode of inductive biases? Like could your like base optimizer have high inductive biases, and then your learned optimizer have like, low path dependent inductive biases?
Yes, this is a really interesting question. So first, I'm going to punt on the thinking about predictive models case, because we are going to talk about that later. There will be a later lecture where we really try to understand, and this is what I've been referring to, hypotheses for thinking about how language models might work. If I just think about the other question, right, which is, the question here is essentially, what if we're in a setting where we learn some model, and that model is itself implementing not just a search process, right? It's a Mace optimizer, but it's implementing a search process over other algorithms. Then that search process might have different safety properties than the original search process. I think that this is a concern. It's a bit of an esoteric concern, because it's a little bit weird why we would find ourselves in a situation where you found a model that is then doing another search over algorithms. But it's totally possible. It's definitely a theoretical concern to be potentially worried about. And it's absolutely the case that you might end up with different properties in the new case, right? So it might be that you have a good reason to believe that the sort of outer thing is doing the right thing, but then once you find another search process, it might not be doing the right thing. This is in fact one of the issues oftentimes with the speed prior in theory, trying to get it to actually work out in the worst possible case. This sort of often comes up. I think that it may be a concern in practice. It's a little bit tricky. I think the way you'd hope to try to resolve something like this is that whatever safety properties we had on the top search, we can somehow transfer them to the next level below. One thing that's really worth being very clear about here, though, is that this is a different thing than the general Mace optimization case, right? The general Mace optimization case is just any case where we're doing a search over algorithms, and one of those algorithms is itself doing like a search over anything, including over actions or plans. And this is a case where we did a search over algorithms, and we found an algorithm that was doing a search, but the search that it was doing was specifically also over algorithms, right? Yeah, okay, yeah, question?
Wouldn't in context learning be an example of exactly this?
Very interesting question. I think it sort of depends on how you think about algorithms. We're going to talk about this later. I think that I would often think about in-context learning as doing a sort of search over conditionals. It's like it has a sort of probability distribution on how it thinks, where it thinks it is, what thing it thinks it's predicting. And then as it gets more information, it's sort of trying to figure out of the various different hypotheses, is this a news article? Is this a fan fiction or whatever? It's getting information that selects between those hypotheses. You could sort of think about those as algorithms in some sense. It's a little bit unclear whether you want to think about it in that sense. But we will definitely return to this later and think about it a bunch more. Yeah.
So this is actually a very basic question, but I just recently realized that I don't have a good picture of the answer. So we are talking about the training where this general intelligence learns models of the world during the training and learns things about how close the proxy objective is to the real one and so on. How should I imagine this training? Is the agent in Minecraft? Is he talking with people? How do we imagine ever teaching it any what do we want about governing a country or a company? What is the training?
Yes, this is a really good question. I think part of the problem of a lot of this analysis is I don't know, We don't know exactly how we're going to train future AI systems and what we're going to train them on. So I think part of what we're sort of trying to do here is do some sort of, well, what's the worst case scenario of the possible things we might ask AI systems for, right? We sort of imagine in this particular setting that we're going to be asking them to do, whatever the most complex tasks are that we want. They require, the most, instrumental reasoning. They require them to be able to do all of these various different things. If we were in that setting and we were trying to train them to do that, what would happen, right? And so, in fact, there's going to be a very large range of things, probably that we ask AI systems to do, that we train them on, that we get them to do, in various different setups, and those might have very different properties. And so, I don't want to, I don't necessarily know exactly what it is that we're going to be doing. I think that in some sense, though, and what I was saying before, if we think about this sort of from an economic perspective, all of these various different use cases, are going to have, reasons why people are going to want to build AIs to do them, right? And so in that sense, we want to try to understand, it may be that 90% of the AIs that we build and 90% of the AIs that we train are totally fine, and they don't have any deceptive issues. But if 10% are deceptive, that might still be a catastrophic problem, right? And so, even if it's only in some individual training cases that this sort of occurs, we might still be quite concerned. And so that's sort of why we're looking at this particular scenario and understanding, okay, what if we were training it to, we trained it on all of the possible knowledge and all of the data that we had available. We trained it to accomplish whatever the most complex goals are that we're trying to get it to do, that we possibly might want out of it, then what would happen? Yeah, question.
I think I understand that part, that now we are concerned about some people trying to build an AI to be a good CEO advisor or politician advisor. That seems the most general thing mostly we can ask for. But then, how should I imagine the training happening? This seems to be some kind of reinforcement learning training we are talking about. It does things. If it doesn't predict the next action, we punish it. If it doesn't do well on the next training task, we reward if it does well, and so on. How should I imagine this being done to a future CEO AI?
Yeah, so I'll point out that the thing you just described is not specific to reinforcement learning. So this is true of supervised learning as well, for example. In supervised learning, we have an algorithm, and we have a particular data set that we want the algorithm to fit well. And then we see how well it fits the data set, and based on the mistakes that it makes, we go back, gradient descent goes back in and it changes it to do better, right? So I don't think that this is specific to reinforcement learning. And it's sort of, as I mentioned in the very first lecture, I think that there are important technical differences between reinforcement learning and supervised learning or other sort of approaches. I think that they're, in practice, often not that important, and the sort of more important thing has to do with the task you're trying to get to do. So a simple example of this is that, let's say I want to solve like a traditional RL task, like playing chess or something. I can actually do that via something that looks more like supervised learning. So if I do something like a decision transformer, where what I have is I actually supervised learn my model to predict what the action would be that would get a particular reward. So I sort of condition the model on observing some reward and then have it predict the action that you would have to take to get that reward. That I can collect just a general data set of a bunch of just like things that I can supervise learn. I just want you to fit the data set of what action would get this reward, and I'm not doing some reinforcement learning thing. And then I sort of just train on that data set. Then effectively, I'm still effectively doing reinforcement learning, even though I'm not literally doing reinforcement learning because I'm still training the model to do a good job in some environment. And so I think that the sort of distinction between in theory, am I using this particular ML method or this particular ML method is not that important. I think that sometimes it can be important and those technical details can matter sometimes, but I think for the most part, I want to elide over them. Yeah, question.
So it seems like the deceptive alignment case depends on the model building up a long-term goal and updating it from the proxy. So there needs to be a point where we have these proxy goals, like somewhat aligned model, and it needs to update it to a long-term goal. Do you have any framework to think about how, or maybe just example thing how that happens? Why would there be a steep decrease in the loss landscape from the proxy to a long-term objective? It seems like you need to implement several things at once to have an improvement, which is long-term objective, plus connected to some circuits that implement instrumental reasoning afterwards with relation to the world model. It seems like you need to move a lot of pieces at the same time to get from a proxy to long-term with all of the deceptive things coming after it.
Yeah, this is a really good question. So a couple of things that I'll say. So the first thing I would say is I think we're mostly imagining this sort of instrumental reasoning circuitry is often already hooked up. It's just hooked up for some non-long-term proxy, right? Like if you think about, you have a model and it's just trying to get like the green arrow, each individual episode. It still has to do instrumental reasoning to get the green arrow, right? It still has to figure out, okay, which paths through the maze are most likely to get me the green arrow. And so it's not necessarily the case that green then has to do like a bunch of additional stuff to like hook it up to the instrumental reasoning, because we're sort of imagining it's probably already hooked up. But it does sort of have to take that goal and make it long-term, make it so now it's thinking about how to get the green arrow as much as possible throughout training and beyond. How difficult is that modification? Very unclear. So one thing that I think is quite clear is that it's sort of this, atomic modification in the sense that once you've done this, long-term goal, then there isn't, this sort of, you then have to keep refining the long-term goal, right? Like we were talking about. Once you've gotten any long-term goal, that's good enough to sort of cause the deceptive behavior in training. And so the key thing is just, how difficult is it to actually add some long-term goal? I think it's unclear. I guess a couple of things I'll say. I think that in some sense, I don't think it's that complex. You just have to, count all of the green arrows rather than just the ones, in front of you. As long as you have the knowledge and understanding of like what it means for there to be a world and what it means for like there to be stuff in the world that you might care about. Picking some of those things to care about, I think is relatively straightforward. But I do think it's quite unclear. I mean, I don't think we really know. Yeah.
I mean, I guess we keep talking about like long-term goals and short-term goals and goals that require instrumental reasoning and goals that don't. But it seems like for the most part, like in current ML systems, the goal that we're training these models for is just like maximizing the log likelihood of some data set. So, I mean, this seems like a goal that doesn't require any instrumental reasoning. And it seems hard to become like deceptively misaligned from this specific goal. So, I mean, am I misguided on this?
So first of all, I think you absolutely need instrumental reasoning to solve the task of predict the internet, because humans do instrumental reasoning. And so if you want to predict what humans are going to do in various different cases, you definitely have to be capable of instrumental reasoning. Now, I do think that it is quite unclear in that case whether you're actually going to learn a deceptive thing. And again, we're going to talk about how that might play out and what sort of things to think about in that case later. But yeah, just to start with, I think that it's definitely not true that you don't need instrumental reasoning to do a good job on predicting humans. You totally do. Okay, we will call it there, and we'll pick up next time.